Welcome to the opening presentation of our 3-day webinar series on virtual PLCs, CODESYS 4, known to most of you by its previous working title CODESYS Go and Engineering with AI. My name is Martin Decker and I'm going to take you on a journey into the world of virtual PLCs. We'll explore what virtual PLCs are, how they differ from what you already know, why they matter for your automation projects, and I'll also answer questions that are frequently asked. The highlight will be a demonstration on this hardware setup I prepared for you, in which I'll bring a virtual PLC to life, teach it everything it needs to know, and finally run a CODESYS application on it, including I/Os, fieldbus communication, and visualization. Virtual PLC sounds a bit abstract at first. Let's take a closer look. Before electricity could be used industrially, mechanical means were the only way to control processes and automate them, at least to some extent. As electrification continued to advance, mechanical and electrical systems became increasingly interconnected. Many of you surely still remember or have at least heard of earlier control technology, such as cam switches from washing machines, as shown schematically here, or hardwired programmed logic controllers with relays, as illustrated here, for example, for an elevator control system from the 1960s. And these systems were very inflexible and time-consuming when it came to modifications, upgrades, or even troubleshooting. Things really started to pick up in the late 1960s when the first PLC, as we know it today, was invented. Specialized, programmable hardware designed for the often harsh environmental conditions, complete with its own I/Os. At first, it wasn't easy at all to get people to grasp this revolutionary concept. As the inventor, Dick Morley, recalls, it was difficult to convince people that a small box could replace 50 feet of cabinets. Let's keep that in mind for later when we get to the virtual PLC. And even though the first models still had a lot of room for improvement, they did have many significant advantages, making their rise unstoppable. Over the decades, PLC technology has continued to evolve. More memory became available, decentralized I/O systems were introduced, microprocessor-based PLCs provided another boost, and various fieldbus systems were developed. And so the transition from mechanical to electrical to the electronic PLC we all know today was completed. Another step in the evolution was the development of the SoftPLC, or software-based PLC. These are PC-based automation systems in which the control logic runs as software on an IPC or standard PC rather than on specialized hardware. Many of these systems also use real-time operating systems to control machines with high precision. And each of these abstraction steps has brought a whole range of benefits: savings on hardware, easier maintenance, greater flexibility, and improved updatability, and greater independence from specific components, devices, and manufacturers. The next step in the evolution of control systems, which we are currently undergoing, is the shift toward virtual controllers. But what exactly is a virtual controller? Now, we've already seen that a physical PLC is a dedicated hardware from a hardware manufacturer running a PLC runtime that's tightly coupled to that very device. A soft PLC takes the runtime and puts it on a general purpose PC or industrial PC. And that gives you more flexibility in hardware choice, but the runtime is still installed directly on a specific machine. It's bound to that host. A virtual PLC goes one step further. The runtime runs inside a container, which means there's a virtualization layer between the runtime and the hardware. You can deploy it, move it, replicate it across any host that runs a container engine. You can run multiple independent PLC instances on one machine, and that's the fundamental shift. So basically, a virtual PLC is a runtime, the same kind of runtime you'd find on a physical controller, but it runs inside a container rather than on a dedicated piece of hardware. And the key idea is abstraction. The runtime is decoupled from any specific hardware platform by the virtualization layer. That means you can run it on standard industrial PCs, on edge devices, even on servers in a data center. It works on x86 and ARM architectures. CODESYS Virtual Control specifically uses container technology, for example Docker, as its runtime environment. This is not a simulation or an emulation, it's a real PLC runtime capable of real industrial communication. Let's have a look at the architecture of what I just told you at a conceptual level. You have a host machine. This can be an industrial PC, a server, whatever fits your setup. On that host, you have a real-time capable Linux operating system and a container engine like Docker or Podman. Inside the container engine, you run one, or like here, more containers, each containing a CODESYS virtual control instance. And each of these instances is a fully independent PLC runtime. It has its own application, its own fieldbus configuration, its own network access. The containers are isolated from each other, but they all share the host's hardware resources efficiently. This is the same principle behind microservices in IT, but here applied to automation. And using an additional abstraction layer, a hypervisor, additional operating systems can run on the host system on which, for example, a required license server or engineering and management tools like the CODESYS development system or the automation server can be run. And the key point here is what this enables at scale. You go from one PLC per box to many PLCs per box, and from hardware-bound deployments to something that's flexible, movable, and manageable with standard IT tools. And this is where IT and OT genuinely start to converge, not just as a buzzword, but as a practical architecture with real-world use cases. And if we think back now to how unimaginable it seemed just a few decades ago to replace massive relay circuits with PLCs that are orders of magnitude smaller, we can now imagine the possibilities that virtualization still has in store for us in the future. Let me make this a bit more concrete. Picture a production line in a car factory with welding, assembly, wiring, gluing, testing, you name it. In a typical plant, you're looking at a couple of hundred individual controllers controlling robots, conveyors, welding stations, quality checks, and so on. Several hundred individual hardware controllers, each in its own cabinet, each with its own wiring, each requiring individual maintenance. That's hundreds of devices to procure, install, commission, monitor, and eventually replace. Hundreds of potential points of hardware failure, hundreds of firmware updates. So the operational overhead is enormous. Now imagine replacing those hundreds of physical PLCs with virtual controllers running on IT-managed servers. The PLC logic is identical. Same programs, same fieldbus communication, same real-time behavior. But instead of hundreds of boxes spread across the plant floor, you have a managed server infrastructure. And the impact is huge. Less cabinet space, less wiring, centralized updates and backups, and your IT team can manage these systems with the same tools they already use for the rest of your infrastructure. when one server needs maintenance, you migrate the containers to another. When you need more capacity, you spin up new instances. This is the shift that virtual PLCs make possible. Now, the automotive example is one pattern, but there are more use cases for virtual controllers. The first is centralization. That's what we just saw. Taking plants full of distributed PLCs and consolidating them onto IT-managed servers. This is the big scale play for factories and large companies. The second is modularization. And this one is particularly relevant for machine builders. If you have a machine with multiple functional modules, you can run each module's PLC logic in its own container on a single IPC. Each module can be versioned, updated, commissioned independently. You change one module, you redeploy one container. The rest stays untouched. The third is refactoring. If you have a complex monolithic PLC application, one that handles HMI, fieldbus communication and application logic all in one project, you can split it into separate containers. HMI in one, fieldbus in another, application logic in a third. And this reduces complexity, improves maintainability, and makes it much easier to extend the system over time. But now I've talked enough, and I'd like to show you the whole thing live on a living subject. And for this, I've set up some hardware here. Essentially a multi-core IPC running Debian Linux with a real-time patch and Docker. Connected to it is an Ethernet coupler and a digital output board. The yellow boards aren't relevant to us right now. They'll be of interest for the upcoming presentation. On this, I'll now set up a virtual controller and use it to access these real I/Os. In addition, and for this purpose, I'll switch to the CODESYS installer. I used the CODESYS installer to install a CODESYS development system along with a number of necessary tools. For example, or necessary add-ons. For example, the CODESYS virtual control for Linux SL, or here the CODESYS control SL deploy tool. This, the deploy tool, allows us to set up our system in the CODESYS development system. To do this, go to the menu, to Tools, and then Deploy Control SL, and in the first tab, connect to the host, our system, via SSH. So SSH must be enabled on the host. I already entered the login credentials and go to connect now. It takes a little time until the connection is established, and once the connection is ready, we can have a look at some general information of our host system. As soon as we're connected, we can already see a range of information, such as the container engine being used, the Linux type and version, and whether Python is available on the device. We need the latter essentially as a bridge between our tool here in the development system and the Linux system running Docker. We'll go through the tabs here on the left-hand side one by one. And in the next tab, deployment, we select which images we want to install on our host system. And all the entries in this drop-down list are generated by the individual add-ons we looked at earlier in the CODESYS installer. For our use case here, we need 3 items. The CODESYS virtual control for Linux SL, CODESYS virtual edge gateway for Linux, and a license server, so the controller runs continuously rather than just in demo mode. For each of these components, multiple versions may be available depending on which add-on versions were installed beforehand with the CODESYS installer. Here I've already pre-installed the necessary images on the system, so I don't have to go through the same process 3 times. And as you can see, in fact, I've installed multiple versions of both virtual control and virtual edge gateway. So now we have everything we need on the system. Now the container images are available, so I'll create instances of them in the next step, operation. Since the license server isn't running in a container but natively on the Linux operating system, it's listed here under services and it's already running. The lower section is where we manage everything that lives in containers. We can also see here that there are already several instances of various products on our host, though they're all currently stopped, except this edge gateway. I come to that later. For our demo, I use the plus button here to create a completely new instance of a virtual PLC, filter the list by runtimes, and give it a name. Hit the OK button, and just like that, we've created a new virtual PLC on the hardware. It takes a couple of seconds again until the new instance is ready on our host, so we just wait for this to finish. It's ready now here, but it's still brand new and therefore needs to be configured. For example, I can choose whether the container instance should start automatically when the host system boots up. Under capabilities, a number of entries are already pre-filled. This ensures that the instance has, for example, good real-time performance or access to the network interfaces to enable fieldbus communication. Otherwise, none of this would be permitted or possible by default in Linux. And thanks to the underlying image, it's extremely easy to update the runtime version of a virtual controller or just switch versions. What is important for us now is first the licensing, so that our virtual controller runs correctly in the long term. To do this, we specify where the license server is running, in our case, on the same host with this IP address. And to ensure we can also communicate with our real fieldbus hardware from within the container, we must explicitly grant the container access to the desired network adapter. Our fieldbus coupler here is connected to ENP3SO, and I select the adapter here and map it to the instance of my container. This gives the container exclusive access to exactly this Ethernet port on that hardware. And here's a quick side note. Of course, it's also possible to connect virtual controllers to the network via VLAN, Virtual Local Area Network, which significantly reduces the number of physical network interfaces required on the host, for example. Well, anyhow, since I also have a web visu in my CODESYS project that I want to display in the browser later, I need to ensure that I can access the corresponding port of the web server inside the container. And to do this, I map the internal port 8080 so that it is also accessible from the outside via port 8080, in my example. And now I save all the settings, and once the settings are safe, I'm going to start this new instance of my PLC. Now as the instance is running, To establish a connection to the virtual controller, we also need a virtual edge gateway, which is also located inside the container network. This is because a regular edge gateway cannot find the virtual controllers. And creating and configuring the instance works the same way as for the virtual controller, which is why I've already prepared it and started the edge gateway here. That's what you already seen before. Now we have everything we need to run the application on the virtual PLC. Let's take a quick look at the application. Here I've connected the digital output clamp via the EtherCAT master. And the corresponding Ethernet adapter is already specified in the master's configuration. Specifically, the ENP3SO we just configured is mapped here or configured here. And in addition, visualization is set up, which we can use to control the real hardware with the virtual PLC right away. Let's log in to the PLC and scan the network. Oh, that doesn't work yet because the virtual gateway is not available yet. So we have to create that one first. Here under the same IP address. And port 1217, the exact port which is also mapped to the gateway's container instance. Now we can select the gateway, scan through it, and immediately find our virtual PLC. And since the PLC didn't exist before, we need to set up a user, or a user management actually. So I select this PLC, try to log in, and get the message that a user management is not yet available. So I first create a user management. And then log in directly to the virtual controller and download the application. And once the application is downloaded, I'll start the application and we'll see that everything is running as desired and that the fieldbus is also functioning correctly here on the left-hand side. Let's now take a look at the visualization in the browser. To do this, I go directly to the mapped port of the host system at this address. I forgot the 0. And immediately see the running LEDs, which are also running here on the real hardware. And we can actually use the controls here in the visualization to operate the output terminal, whether it's the speed to slow it down, the direction of rotation, or shutting it down completely. So we can see that just in a few steps, we've gone from 0 to setting up a new virtual PLC and getting an application, complete with fieldbus communication and visualization up and running on it. To conclude the live demo, I'd like to stop the container instance of our PLC to show that CODESYS immediately loses the connection and also stops the application, including web visualization and IOs immediately. To do this, I go back to the development system, to the deploy tool, and stop my virtual PLC. I immediately get the message that the connection was interrupted, and as you can see, the LEDs also stopped flashing. Well, now that you've gained a basic understanding of how our virtual control works, you may have a few questions. And that's why I like to address some of the questions we get asked most often. First, is the virtual controller just as powerful as a native one? And the short answer is yes. We've done measurements under realistic real-world conditions, and the virtual controller delivers performance on par with native controllers. It is just important to properly configure your Linux system regarding the real-time capabilities. Second, how many instances can I run? That's a classic. It depends, but our recommendation is to dedicate one CPU core for housekeeping. That's the operating and the container engine basically, and then one additional core per virtual controller instance. And this core pinning can also be done in the deploy tool like we saw in the live demo. On a question that's particularly relevant for IT teams and DevOps workflows, can you manage virtual controllers without the CODESYS development system? And yes, this is a major advantage. The deploy tool in the development system is actually built on a Python script, and that script can be operated directly from the console. You can script it, automate it, and integrate it into your own pipelines. We provide documentation for this, including specific use cases showing how to automate the underlying processes. Communication with the outside world. You likely saw this in the demo already. The necessary resources, such as network interfaces, are passed into the container, and from that point on, the virtual controller uses them exactly as a native controller would. We sometimes get asked whether the container images are available for direct download somewhere. And the answer is no, not at the moment. They're currently distributed as CODESYS packages through the CODESYS store or the CODESYS installer. Nevertheless, we're exploring ways to make them available through other channels and repositories in the future. And finally, licensing. How does it work? How much does it cost? Well, you need a license server, and the virtual controllers automatically borrow their licenses from that server, and the assignment works reliably. There's currently no scenario where controllers claim the wrong or miss the correct licenses. And one important detail, the license server must run natively, not inside a container, but it doesn't have to run on the same machine that hosts the virtual controllers. Any system in the network will do. And regarding the pricing, the licensing is based on application-based metrics. The licensing is structured by application characteristics, not by hardware or by instance count. So you choose a tier based on what your application actually needs. How many field buses, how many I/O channels, whether you need dynamic C core or task group assignment. The tiers range from Control Basic S up to Control Performance XL, and every tier includes 5 years of runtime updates, Visualization S, Communication S, and a Data Source Manager license. So you pick the tier that fits your application, and that's your per instance cost. It's predictable and it scales with complexity, not with the number of boxes on your floor. And in addition to this flexibility in licensing, there's a whole range of other key benefits. You're hardware independent, can scale your system with extreme flexibility, and operate cost effectively thanks to reduced hardware requirements. You can deploy your virtual PLC on all different kinds of devices and systems and move instances freely between them. And on the operation side, you have simplified maintenance, security by container-based design, and an improved tooling for your development team. Plus, fewer devices, less wiring, container-based workflows. So it all adds up to a fundamentally more efficient way to run industrial control. So after taking in so much information over the past half hour or so, let's take a moment to catch our breath. We're almost at the end. To wrap things up, I'd like to share the most important key takeaways with you. A virtual PLC is a real runtime that runs in a container. It's not a simulation or a mere fantasy. It can be used in the real world, and it is. The workflow from initial setup to final productive operation is just straightforward. You can run multiple instances on a single piece of hardware. Full industrial capability is there from the start, for example, regarding fieldbus communication or visualization. And the benefits we've just seen aren't just future promises, they're already reality today. That's why my message to you is, try it out for yourself. You can get the CODESYS virtual control from the CODESYS store or through the installer. I've listed the link here in the presentation. For documentation, check the CODESYS online help at helpme-codesys.com. There look under Products, Control, Linux-based runtime systems. There are also specific use cases with detailed descriptions. And for video tutorials, visit our YouTube channel. That's all from me now for the first webinar in our series on virtual PLCs. In the next webinar, you'll learn how safety PLCs are undergoing a paradigm shift. And in the coming days, you'll learn more about CODESYS 4 and AI in CODESYS. If you have any questions, feel free to reach out. You'll find contact information in the video description below as well. Now, thank you for your time today and enjoy working with CODESYS.